This is Lesson 1 in Unit 10. Today we're going to talk about series and convergence. An infinite series is defined as the summation of a sequence with an infinite number of terms. In other words, if a sub n is our infinite sequence, then the summation from n equals 1 to infinity of that a sub n term is found by adding a sub 1 and a sub 2, a sub 3, and so on and so forth. An infinite series. We will find that when a sequence of partial sums converges, then the series will converge. In this lesson, we'll look at geometric series and telescoping series. And in the next lesson, we'll look at p-series and harmonic series. Infinite sums are called series. An infinite sum is called a series. This is a series. And you can see that I'm substituting 1 for n, and then 2 for n, and 3 for n, and so on, and summing up the nth term where n is infinity. In the sequence, that is adding up 1/2 is s sub 1, and 3/4 is 1/2 plus 1/4. That's s sub 2, and 7/8 is found by adding s sub 1 and s sub 2 and s sub 3. So this is the sum of this nth term sequence. And the value of a series is the limit of the sequence. So the value of the series is the limit of the sequence. Let's look back to some previous courses. If we want to write the indicated partial sums for the series, s sub 1, we would substitute 1 for the n in this place, in this a sub n term, and we'd get 1 over 2 to the 0 power, which is 1. If we want to find s sub 2, or the partial sums for the first two terms, that would be 1 plus adding a 2 here, so that would be, so that would be a 1 here, s sub 2, and that would be 2 minus 1, so 2 to the 1 power, or 1/2. So our s sub 2, or second partial sum, would be 1/2. S sub 3 would be 1 plus 1/2, and then again putting a 3 here, that would be 2 to the second power, which is 1/4. So that would be 3/2, so 4/4 and 2/4 and 1/4 would give us 7/4 for that third partial sum. And then our nth term would be 1 plus 1/2 plus 1/4 plus 1/8 plus 1 over 2 to the n minus 1 power. Here are the definitions of convergent and divergent series. For an infinite series, the nth partial sum is given by this expression. So we know that we're going to add that up, that series. If the sequence of partial sums converges to a number, then the series converges. The limit of the partial sum, the limit of the sum is called the sum of the series. If s sub n diverges, then the series will diverge as well. Geometric series, again, this is just review. A geometric series can be written in two different ways. If you start with n equals 0, then you can write it this way, provided that first term isn't 0. Because if the a term is 0, then every term is 0. And this is probably the more familiar, starting with the lower bound at 1, you want to force the ratio to go to 0, so we need n minus 1 in the power. Either one of them is accurate, but you've probably seen this one more than the other. For convergence of a geometric series with the ratio r diverges regardless of the sign of the ratio, whether it's positive or negative. So the series will diverge if the ratio is bigger than 1. And if the series is a fraction or between 0 and 1, then the series converges. And if it does converge, if the ratio is in between 0 and 1, you can find the sum of the series by using this formula here. And if we want a partial sum of a geometric series, you can use this formula, you can use this formula, or you can also break it apart to be a sub n over 1 minus the ratio minus a sub n r sub n over 1 minus r. I said a sub n, I meant a sub 1. We're going to call, let's back up a minute. I got ahead of myself. Let's call this the geometric series test, because often through this unit you'll see me write GST for geometric series test, and we'll see this again in our second lesson. Just make a note of that. And then on to example 2. Again, it's review. We want to consider the infinite geometric series. The first term, a sub 1 term, is 8, and the ratio looks like it's 1/5, because this is 8 over 5 to the 0, 8 over 5 to the 1, 8 over 5 squared, 5 cubed, and so forth. If we want to write the infinite series using summation notation, I can write that as the sum, as n goes from 1 to infinity, of a times r to the n minus 1 power, and I'm using that more familiar pattern, the geometric series at the top. We want to find the fourth partial sum, so the fourth partial sum would be adding these 4 terms, so 8 plus 8/5 plus 8 25ths plus 8 over 125 is our fourth partial sum, and using my calculator I get 1248 in the numerator with a common denominator of 125. In part E, we want to find the infinite sum. So the infinite sum S would be using the formula a sub 1 divided by 1 minus the ratio. And a sub 1 was 8, and our ratio was 1/5. So 8 divided by 4/5 is 10. So our series converges. And we knew that because the ratio was 1/5, and that was between 0 and 1. On example F, we want to find the limit. So the limit as n approaches infinity, we said that would be a sub 1 over 1 minus r. And in this case, we know that it goes to 10. So the limit as n approaches infinity of our s sub n is going to be 10. And that backs up why we know we have convergent properties there. Example 3, we want to find each if possible, and if not possible, to explain why. In part A, the first piece we have is, we want n, it's 0, so this is going to go to 1, so this is 2, and our ratio is 1/3, so 1 minus 1/3, and 2 divided by 2/3, that's going to be 3. And in this case, when n is 1, we have 1 in the numerator and 5 in the denominator, so we have 1/5. And the ratio is 2/5, so 1 minus 2/5 would be 3/5. And 1/5 divided by 3/5 is going to be 5/15, which is 1/3, so 3 1/3 We've got 10/3 for the summation there. In this case, I see two different things. We could rewrite this as two summations. So as n goes to infinity, from 0 to infinity, the first one is 4/5, and I'm going to group that together to the nth power. And then the second one, we're going to have 0 to infinity, and it's subtracting here. And then 7/5 can be raised to the nth power. Now, considering this first infinite series, our ratio is 4/5. And with the ratio 4/5, we have no problem. But in this one, we have 7/5. And in that piece, when the ratio is 7/5, that's bigger than 1. So this one diverges. And because that one diverges, then we can't have something that converges adding to something that diverges when we put it back together. So this would be a divergent series. Here's a couple of properties. Given that two convergent series, the sum of a sub n and the sum of b sub n, where a, b, and lowercase c are real numbers, if the summation of a sub n is capital A and the summation of b sub n is capital B, then the following series converge to the given sums. So in this case, we're able to take the summation of a sub n and bring that c value, that real number, out in front like a multiple and multiply it by the summation after we're finished. In the other two properties, we've already seen this in the previous example, you can rewrite that infinite series as two separate series, find each summation, and then add them together or subtract them, as the case may be. Let's investigate a fun series where the terms collapse like an old-fashioned spyglass or telescope. Whoop. This type of series is not used very often, but they're sort of fun to consider. So here in this case, we need to use partial fractions. We learned that in a few chapters ago by rewriting things. So we could rewrite this term as 1 over n times n plus 1, using that property of partial fraction decomposition. And if our numerator is combined, and we let n be -1 to kill off this term, then -1b is 1, so b is -1. And if we let this term n be 0, so this term goes away, and this is 0, then 1a is 1, so a is 1. That gives us the right to rewrite this summation as two different expressions. This would be 1 over n when a is 1, and then we're going to subtract from 1 to infinity 1 over n plus 1 in this second case. And then we want to jump in and start to substitute. So if we look for this first term, when n is 1, this term is 1. And when n is 1 here, this is -1/2. And then back to this one, when n is 2, we have +1/2. And when n is 2 here, we have -1/3. And you can kind of see where this is going. When n is 3 over here, we have +1/3. And when n is 3 over here, we have -1/4. So as that pattern continues along, and we get up to the -1 over n and the +1 over n, and then the next term is going to be -1 over n plus 1. So you can see what we're talking about when we talk about telescoping. This term stays, but these two add up to 0, and there's a 0, and there's a 0, and there's a 0, and then this term stays. So when you follow through that progression, we're going to find out that this is totaling 1 minus 1 over n plus 1. And if we take the limit of that summation and consider this, we've got this limit at infinity is 1, and when we have 1 divided by an extremely large number, this term goes to 0, so our limit is 1. And we used partial fractions to find the sum of the series, and the sum of this series, which was a telescoping series, is 1. Example 5, given this sequence, we want to explain the difference between the sequence a sub n and the series, which is the summation of the sequence. So the sequence, we said earlier, is the terms a sub n. So a sub 1 would be 1 times 2, and a sub 2 would be 1 over 2 times 3, and a sub 3 would be 1 over 12, and so on and so forth. So what happens? The sequence is going to converge if its terms approach a specific value as we progress through all of the values up to infinity. So do you see a pattern here? 1/2, 1/6, 1/12. In other words, each term is getting smaller and smaller, and if we took the limit at infinity of that a sub n term, we're going to see that the numbers are approaching 0, so the sequence is going to converge to 0. And then the series, we said by definition the series was the summation from 1 to infinity of the a sub n term, 1 over n times n plus 1. So we would take each term, 1/2, 1/6, 1/12, and continue on until we added to infinity. Now I happened to use my calculator and found that the sum of that infinite series is equal to 1. So the numbers add up to, the sum of the series adds up to 1, but the sequence in the series, as you approach infinity, those numbers are converging to 0. Example 6, we want to write a geometric series for the repeating decimal 5/100ths. So if you rewrote 5/100ths, expand it out a little bit, you can see a pattern that develops. The first term would be 5 over 10 squared to get 5/100ths, this number here. And then if we go to the fourth decimal place, we got 5 over 10,000ths, or 10 to the fourth power, and then 5 over 10 to the sixth power, and you can see that pattern develop as we go on. So our a sub 1 term is 5 over 100, and our ratio is 1 over 100, or 1 over 10 squared. That tells us that the summation from 0 to infinity is 5 over 100 times 1 over 100. And if we put a 0 up here, this expression, this a sub n term, will produce that first term in our sequence. So 5/100ths can be summed up using the formula a divided by 1 minus r. And we said a was 5 over 100, And we had 1 minus r, which was 1 over 100, which gives us, what, 5 over 100 divided by 99 over 100. So 5 hundredths repeating is equivalent to 5 99ths. Now, the nth term test for divergence, I like to call this the divergence test. Divergence test. Some textbooks will call it the zero test. And also the nth term test for divergence. But basically it says this: if a series converges, the limit of its nth term must be 0. And we can say that mathematically this way. Now, the contrapositive, this is why I like to call it the divergence test. The contrapositive gives us a useful test for divergence. That's the intent of it. And that contrapositive basically says, if the limit does not converge to 0, the series has to diverge. So one important piece of information that I want you to remember is that this test, the divergence test, is inconclusive. Is inconclusive if the limit as n approaches infinity of a sub n is 0. So if we take the limit of the a sub n term, or the a sub n expression, and we get 0, we may or may not know it converges. We will need some other test besides this test. So this test is for divergence. Let's look at 3 examples. We want to determine whether the series converges, diverges, or we're not able to tell. So in this case, remember what we're doing is we're taking the limit as n approaches infinity of this a sub n term. And you could look at that a sub n term in a couple of different ways. It just depends on what you like, which method you like to use. So you can think of it as the dividing out technique, where we're multiplying the top and the bottom by the highest agreed term in the bottom. And I tell my students this is the dividing out technique. So n squared times 1 over n squared gives us 1, and 5 n squared divided by n squared is 5, and 4 divided by n squared is 4 over n squared. And taking the limit at infinity shows us 1 and 5 and 0. So we get a limit of 1/5. And 1/5 isn't 0. Therefore, we can say that our a sub n diverges. The test is conclusive. It's the divergence test. A sub n diverges. The test works. The test tells us we have a divergent series. In part B, another approach, remember we're looking at the limit as n approaches infinity, and we've got n over n cubed plus 1. So another approach, since we're approaching infinity, adding 1 to infinity won't change that problem very much. But if we think about the numerator power is n and the denominator power is n cubed, then you could simplify that down to 1 over n squared. And the limit of 1 over n squared, so I've got a 1 divided by some incredibly large positive number squared, we're going to get 0. So here's where you don't want to get fooled. This is a divergence test. And if I call this my b sub n, if this is b sub n, then I know b sub n may or may not converge. The test is inconclusive. The divergence test is inconclusive. We need more information, right? And then part C, whoop, you'll see in the next lesson, I believe, that this is going to be the harmonic series. So taking the limit as n approaches infinity of 1 over n, again, 1 divided by an incredibly large number is 0. So the divergence test doesn't apply, and we could call this the C sub n term. So therefore, C sub n, C sub 2, C sub n may or may not converge. We need more information. We're not able to determine that yet. Another thing you might want to consider, I didn't do it on part B, but think about this one. If we considered the series, you can see what's happening. You've got 1 plus n is 2, that's 1/2, plus n is 3, that's 1/3. You see that I'm adding up to a number. So there's not enough information to know yet, and we'll see later on when we talk about harmonic series what's going on. Okay, in the last two examples, this is a little backwards thinking. We have the nth partial sum given, and here's our nth partial sum, and we want to find a rule for the a sub n term. So we don't often see that. But the big idea here is, let's think about the summation. If I knew a sub 1 and a sub 2 and a sub 3, and I went all the way up to a sub n minus 1 and then a sub n, so I'm looking for this term, but I don't know all those terms. How would I find those? So one train of thought is, if this is the summation of the n minus 1 term and all of them are the s sub n term, then we could find this one by taking, if I want the a sub n term, I'm just going to take the s sub n term and subtract the s sub n minus 1 terms, and that would leave me this term all by itself, because I'm just going to get rid of all of those, and then I would know those. So that's the game plan. And if we put that together mathematically, we already know s sub n, that's n plus 2 divided by n plus 5. So the quantity n plus 2 divided by n plus 5. And then what would this term look like? It would be the term right before this, so n minus 1 plus 2, and then n minus 1 plus 5, because that's the term right before the one we want. So we could neaten this up a little bit and then find a common denominator. This numerator would be n minus 1 plus 2, so that looks like n plus 1. And this one would be n minus 1 plus 5, so n plus 4. And then our a sub n term that we're looking for would be n plus 2 times n plus 4. So n plus 2 times n plus 4. And we want minus n plus 1 times n plus 5. And then we would have the common denominator, n plus 5 times n plus 4. So using distributive property, we got n squared plus 6n plus 8 minus n squared minus 6n minus 5 over that common denominator. And then collecting like terms, it looks like our a sub n term is going to be 3 over the quantity n plus 5 times n plus 4. In example 9, it's similar to 8, just a little bit easier. We want the nth partial sum of the series, and we know that this is the S sub n formula, and we want to write a rule for the 6th term. So the sum of the first 6 terms are the first 5 terms plus the 6th term, and if I want just the 6th term, I can take this summation and subtract the first 5, and we would know the 6th term. So in order to do that, we can say that the a sub 6 is, using this formula, 6 squared plus 2 over 6 plus 1, and then using that formula again for 5, that's 5 squared plus 2 divided by 5 plus 1. So the 6th term is going to be 38 over 7 minus 27 over 6. And if 42 is my common denominator, we could have 228 minus 189, so 39/42, or if you wanted to reduce that down, you could divide by 3, that would be 13/14. And that is the end of lesson 1.